Wow. All right. Well, thank you, Charles. I don't know if I deserve all this stuff that he said. And thank you very much all for coming. I know it's a busy day. Fridays are always, packed with things to do and the upcoming weekend. So thank you very much for coming. So Charles and I first met at American Chemical Society, and I've always been, we've always stayed in touch, and I think he's going to be a big asset to the university in the coming years. So you guys should definitely interact with him as well. And also, thank you very much for all the professors and the provost and the dean and wonderful people, the chair of the chemistry department, everyone who came for this talk. So what I'm going to today talk about is, I know there's different people with different backgrounds here. So it's going to be more, in some ways, more generic. I want to kind of give some broad strokes of the kind of research that we do and how it may affect different fields. And really all of it revolves around this kind of problem where, when I made this slide, it literally took me 2 seconds to see many examples of this. So this is, there's a big problem in medicine today. I need to stand far away from this. I was told about that, but it worked for you when you were closer. Okay, how's that? All right. Maybe I talk loud. Maybe I should. Maybe this works if I just hold it. I don't know. Maybe. I apologize anyway. But this is a big problem in medicine, basically, where there's lots of people who have lots of different kinds of diseases because of failing organs. So many of you guys may have known someone, or some people may actually have family members who have different kinds of diseases, ranging from diabetes to heart disease to liver disease, where the organ is actually failing. And what really people have seen in the past, since actually the first transplantation happened at the hospital where I partially work, and that was kidney transplantation. So since that happened in, I believe, 1956, so since then, there's all kinds of transplantations that are happening in the world, and there's a lot of diseases that are being kind of treated. But what the problem still remains is that for someone to get better requires someone else to actually die, because you need to get the organ. So this is a big problem in many of these cases. So when I was trying to dig up this slide, search for it, it took me 2 seconds to come up with some examples. So this little girl here needed a heart transplantation to kind of survive, and they were trying to find one. And this guy here actually had kidney disease, and then he won the lottery, and then he got all these people offering to give him the kidney because for some money. So there's a lot of problems like this. But what people, engineers and biologists and different kind of people who are interested in this problem have tried to do is to try to come up with ways where we can engineer artificial organs outside the body. So you guys have heard about a lot of artificial implants, which are mostly made just from materials like, let's say, hip replacements and things like that. Many of those materials are just what they are, materials, and not really biological substitutes. So what people have been trying to do is actually come up with tissues or biological substitutes that can address this problem. So how do we actually make tissues that look like real tissues, they get integrated into the body, and actually treat the disease that we're trying to do? So one of the ways that people have been working on is this thing called tissue engineering. And the general idea with tissue engineering is, can we try to take cells and somehow put them together in a way to actually try to create an artificial tissue? So the most kind of standard paradigm here is people take cells and different kind of biomolecules or growth factors that can affect cell behavior, and put these cells and growth factors on top of a degradable scaffold. These scaffolds, you can think of them as degradable plastics that are very porous, So what happens in these porous scaffolds is that you can put the cells and these growth factors, and then the cells start rearranging themselves and start degrading this plastic foam and generating things that looks like three-dimensional tissue. So and sometimes you put them in these bioreactors, and once you get a tissue-like structure, then you can potentially transplant it. And the cells here are can come from the patients themselves. They can come from other people. They can potentially come from stem cells and other sources. And this is why stem cells have generated so much interest, because if you can actually generate cells that can go into this process, then potentially you can treat a lot of different types of diseases. So there's been some examples of this kind of process actually working. So, for example, burn patients. So there's a number of different products out there where people take skin cells and grow it in a culture outside the body to get sheets of skin cells. And then what you can do is that if you have a burn patient, then you can put this artificial skin on where the burn is. And this kind of process is already kind of being done at hospitals. But for more complex tissues, beyond skin and beyond very simple tissues, tissue engineering hasn't really become a successful product or successful approach. Because of the fact that your body is very, very complex, the way nature makes a biological organ is not very simple. And even when you get a lot of people from a lot of smart people, engineers and biologists and material scientists, all trying to solve this, we still can't mimic what nature does. So some examples of how people make this. This is one of these degradable plastics which I mentioned that people put on, people can mold in the shape of different kind of tissues. So this one is obviously molded in the shape of an ear. Then you can put cells, cartilage cells that actually make up the ear cell types. And you can put them, these cells, on these degradable scaffolds, kind of adhere, align, potentially start connecting with each other, and degrading this scaffold so that you have something that looks like an artificial ear. And when I was starting to think about what I wanted to do, when I just graduated, this is, as Charles mentioned, I graduated in 1999 with my bachelor's. There were things like this. This is a cover of Time magazine where they discussed the hottest jobs of the future. And actually they had listed tissue engineering as the #1 job of the future. So it was like, even back then, it was very futuristic and very kind of powerful and potentially game-changing area. But despite all this, there's been some successes, but still there's a lot of challenges in tissue engineering. So some big challenges about how we do this, for example, are things like how do we actually get the cells? So when I first started thinking about this field, there was no human embryonic stem cells, and people didn't know they could be derived. They definitely were not these induced pluripotent stem cells. These are stem cells that you can get from your own skin, and you can reprogram so that they can become like very primitive stem cells. And this field has really gone forward a lot, and it's, I'm sure you guys have heard a lot of these things in the news, but it's still lots of challenges in how do we take those stem cells and generate the cell types that we want. So if you want to make a heart, you want to not only have stem cells, but you want to have heart cells. So how do we try to get these stem cells to become heart cells? Because your body has over 200 different cell types, so if you need to get one of those cell types, then how do we actually do it? Because these stem cells, at least the early embryonic stem cells, can differentiate to all of those different cell types. So you really need to understand how to direct their behavior. Another big problem is vascularization. If you have cells that are more than a couple hundred microns, smaller than the width of your hair, away from a source of oxygen and nutrients, which occurs like in your blood vessels,